Okay. Yeah, thanks. Hi, everyone. I'm Pierre, so I'm going to talk about MCMC, Markov Chain Monte Carlo. So we have four sessions on that. So hi, everyone. Don't hesitate to interrupt at any point to ask questions. And so let's get started. So I'm going to talk about MCMC. I'm going to assume that it's not a familiar topic to you all, at least, but I've put stuff that are more advanced, stuff that are more basic, so let me know when you want me to spend more time. So I'll talk about the very basic to begin with, the motivation. Then we'll talk about some examples of those algorithms. So it's a class of algorithms. There's many, and I'll just talk about some of the more familiar algorithms for the statisticians / econometricians. But I'll talk about the fact that it's a class of algorithms that was mostly developed in physics, and it has many other applications in chemistry, in molecular dynamics in particular. So just focus on I think, the ones that are more useful for econometrics. Today we'll talk about some of the outstanding questions, which hopefully we'll try to address in the next few days, in particular using so-called couplings. But today we'll talk about the basics. So the goal is to obtain samples from a probability distribution. So I'll denote by pi throughout yeah? Oh yeah, sorry. Up. Talk about the task of obtaining samples from a probability distribution. So I know Guillaume mentioned R. You're more like R users or Python users. It's the same. Obviously, you can code in any language. In R, for example, the normal distribution would be available through the density function. It's called dnorm. And you can also obtain sample using rnorm, right? So there's a function already made for you, so you don't have to do MCMC. So the problem is that in general, if your distribution is not just a normal distribution or gamma or a well-known distribution that has a Wikipedia page, then the problem of obtaining samples is not super generic. It's not a solved question. And so there are many ways of obtaining those samples. And often we are not directly interested in obtaining samples. We're more interested in obtaining integrals, or computing expectations or integrals. So here I denote by h of x, the expectation of the variable h of x. So x would follow pi, and h would be a so-called test function. So to give an example, maybe you're interested in computing the probability that the distribution pi assigns to a certain set. So the probability that your test statistic is in the rejection region, for example, if you're doing a test. And so that would be, x would be your test statistic, but h would be the indicator that this test statistic is in a certain set, the rejection region. So in general, there's a function h. Maybe it's just the identity function also, that's a usual case, and then you're interested in obtaining the expectation of x. Okay? And so with different choices of test function, you access different aspects of the distribution, all the moments, for example, the variance, and so on. And so the notation would be, assuming the state space is continuous, so integral of h of x pi of x dx, so that would be a continuous state space, while the distribution pi would have a density, denoted by also pi, as an abuse of notation. But in fact, it could be that the state space is discrete. It could be that it's a mix of discrete and continuous components. Right? So using quite a generic notation that is supposed to encapsulate various cases that might be of interest. And so the general problem is called sampling or numerical integration. So how to numerically obtain those integrals. And generally, we resort to so-called Monte Carlo methods to do that. There are other methods also. And so why is it interesting in econometrics and statistics? So people may be more familiar with the problem of optimization because the estimators typically are defined as the solution of an optimization program, just like what Guillaume was presenting in the case of quantile regression. So in general, you could imagine M estimation, where you're trying to minimize the sum over the data points of a function of some parameter theta, so that would be the betas in the previous talk, and that depend on the data. That could be just y's or y and x's, for example. And so it's quite obvious that numerical optimization is useful in econometrics and statistics. It may be a bit less obvious why integration is also helpful. So I'm going to give a few examples as to why I think optimization is helpful also in combination with integration. So in particular, it could be that your objective function, the little m function here, involves itself an integral, for example, over latent variables. Right, so itself, the m function might involve, so it might be, for example, a log likelihood, or the minus log likelihood, but the likelihood itself might involve latent variables. So for example, I'll give some examples later on. But there are all classes of models, such as state space models, for example, in time series that involve latent variables. And so then you might have an integral that you don't know how to solve exactly, and that might require some numerical integration. And so then you may be familiar with expectation maximization as a way of obtaining the maximum likelihood estimators in models that have latent variables. And in expectation maximization, you would alternate between essentially integrating the latent variables, u, and optimizing over the parameters. And that's only useful if you don't know how to do that integral analytically. Otherwise, you can just think that you have this there's an integral here, but you solve it, you have just a function of theta, and you maximize that. But sometimes you don't know how to obtain that integral exactly. You don't have an analytic form from it. And so then you resort to, for example, the EM algorithm, which itself, in fact, can be seen as an optimization problem over two components, the parameter theta and a distribution Q, which is a distribution of that latent variable. So there's a way of seeing, so this is a bit of a complicated optimization problem now because one of the coordinates is a distribution. Okay? But so the EM algorithm is trying to do at every step an optimization of a Q given theta and optimization of theta given Q. There are references here. Okay. So there are also estimates that are directly defined as expectations. So typically in Bayesian inference, for example, if you're familiar with Bayesian statistics, you would put a prior distribution on the parameter space. So the parameter now is a random variable. So prior distribution typically is a way of incorporating some information that you have prior to the data into the problem. So maybe because you had done some previous analysis of a similar type of problem that translates now into a prior distribution. So you know the parameters, for example, of your regression. After some previous studies, you know that they may be positive already, for example. And so you can incorporate that into the prior distribution. And then you have the likelihood function. You multiply the two, the prior density and the likelihood, and you obtain the posterior distribution. And then if you want a point estimate from that, instead of having you have a whole distribution of parameters, but you may want to summarize it. And so then, for example, you can take the posterior mean, and that, by definition, is an expectation. So here are references in the econometrics literature that employ MCMC to obtain estimates that are defined as expectations. So far, so good? Okay, so hypothesis testing also. So typically you want to compute some p-value, and that is defined as a probability of observing a test statistic that would be at least as large as the one that you do observe under the null hypothesis. And so often, because you can resort to an asymptotic reasoning that tell you that this is a chi-square distribution or a mixture of chi-square distributions. So then again, you don't have to do Monte Carlo because you know a lot of things about the chi-square distribution. But believe it or not all test statistics follow a chi-square distribution. They may follow a very complicated distribution. And then again, in order to compute the p-value, now you have a numerical problem to solve. So those are two references. So the first one is lecture notes explaining various uses for MCMC in hypothesis testing, and a recent one in analysis of stats. And I'm putting that just to say that even if you're firmly against Bayesian inference, and some people are very firmly against Bayesian inference, because this notion of prior distribution sounds like, for some people, it's against the objectivity of science, and so on and so forth. I'm mostly going to talk about the computation, so I'm more agnostic to that debate now, but it is a very big debate in statistics. But I just want to say with this slide that even if you're not interested in Bayesian inference, you may still have some numerical integration problems to solve. For example, in hypothesis testing, which is really on the opposite end of the spectrum than Bayesian inference for the statistician. Okay. So if you do want to do Bayesian inference, then typically you have integrals coming up for the posterior distribution, but also when you do model comparison. So for example, the BIC criterion, the famous model selection criterion, is an asymptotic approximation of the so-called marginal likelihood. So that's the denominator when you do Bayes formula with the likelihood and the prior. And the denominator itself is used as a model selection in Bayesian inference. And so sometimes it's convenient to do the BIC, so the asymptotic approximation when you have a fixed number of parameters and a lot of data. But in some other cases, maybe you don't have that many data points or the parameter space is very large, then BIC is very inaccurate and you may want to actually compute directly that marginal likelihood. So this is again a reference. I'll try to put reference in econometrics more, assuming you're more in econometrics than I am. Just to say that there is a lot of econometricians interested in those Monte Carlo questions. Okay, so actually I was also trying to link with causal inference in a desperate attempt to connect with the different parts of the title of the summer school. And so it turns out there's an active also research in MCMC, in causal inference, and that has to do with trying to find directed acyclic graphs that may be compatible with the data, because typically there's many of them, not just one. So finding the one point estimate may be a bit misleading. You may have lots of different graphs compatible with the data, so you may want to average over all those graphs instead of selecting one in particular. And then the Bayesian approach is a way of formalizing this sort of model combination, if you want. So there are papers, for example, operating on the space of direct acyclic graphs or different representations of it. So here are some references. And in the potential outcome framework, then you may want to do a Bayesian inference again. And so here are papers arguing that some recent causal inference competitions, the winners of those competitions have employed Bayesian non-parametric approaches, which again in practice means running some Monte Carlo algorithms to obtain the numerical answers. Don't ask me too many questions about the content of this article. Okay, so taking a step back, the Monte Carlo methods originate in physics, very much in the sort of Los Alamos, Oppenheimer type of setup. And it was a realization that a lot of computations cannot be done exactly, large sums, integrals, but using random variables, you can usually get a reasonable estimate of the quantities of interest. So I'll mention the original paper introducing the first MCMC algorithm in a few slides. And you can find now entire books dedicated to the problems, such as the Handbook of MCMC. The reason why it's popular is that in some sense, when you're integrating over a large dimensional space, Monte Carlo methods achieve the best possible rate of convergence that you can hope for. So there are results, for example, in Novak that says that compared to all the other ways that you could go about numerical integration, Monte Carlo is going to give you the optimal rate as the dimension goes to infinity, and assuming that you don't know anything about the test function, which is not true necessarily in practice, but in some sort of limiting complicated regime, this is the best way of doing numerical integration. So other ways of doing numerical integration would be, for example, if you have a one-dimensional integral, you want to compute the area under a curve. You know, naturally in high school, you may decide to grid the space, obtaining, for example, equidistant points on the space. You compute the value of the function there, and then you're going to approximate the volume, the area under the curve by for example, the volume of a sum of rectangles. Okay, and as you put more and more points, it will converge to the area under the curve. And you can see here that the smoothness of the curve will have an effect on the precision of your estimate. Right? You need more points if your function can go and wiggle about everywhere. Okay? And so in dimension 1, in fact, you should not do Monte Carlo. This will not give you the best rate of convergence. This equidistant point method would probably be better. It would converge at a rate of order 1 over the number of points, whereas the Monte Carlo method would converge at a rate of the order of 1 over the square root of the number of points. Okay, so in dimension 1, you should not use Monte Carlo. But this Novak paper, that is a review paper on the problem, would tell you that if you were in a d-dimensional space, where of course doing grids usually involve a lot of points, right? Exponentially many points, then it would be better to do Monte Carlo than any grid-based methods. Even though they are very smart grid-based methods, I must say. So if you're in dimension 5, for example, it's kind of up in the air. If you're in dimension 2, probably still smart grid-based methods are better. But as far as I know, in dimension more than 10, quite often in econometrics and statistics where the dimension corresponds to the number of parameters, then Monte Carlo achieves the best results. Okay. But it's not by any means the only method. So recently there was also a lot of interest, there is a lot of interest in the links between sampling and optimization, so I'll give a few pointers on that. Because sort of naively people thought maybe optimization is fundamentally simpler than integration. It's faster to obtain the MLE than to do Bayesian inference, for example. In fact, it's quite a complicated question, and so there's been a lot of interest in that question, trying to compare the difficulty of solving the optimization problem numerically and the difficulty of solving the numerical integration problem. So I'll try to give a few pointers along the way. Okay, so Monte Carlo methods are algorithms. So there's going to be some inputs, outputs. There's going to be some tuning parameters often that we'll have to choose. So we'll try to think about optimizing the performance in a way, and the performance will have to do with the cost of running the method, and then the precision of the output, the precision of the estimate. So inverse CDF transform, Guillaume mentioned it. So if you want to sample from pi, obtain x from pi, and maybe you have the quantile function, so I'm going to denote it by q, and you plug a uniform sample in that quantile function, and that is distributed. If this is the quantile function of pi, of course, then that is distributed according to pi. Okay, so you could say, okay, problem solved, then why are we doing anything more complicated than that? Any guess, again? Why may we not do always this to obtain samples?
You won't always have such a closed, nice form of pi that you can invert.
Yeah, we may not have access to this, and in particular when the distribution is not in dimension 1, even defining this becomes more tricky, right? The multivariate quantile functions. In fact, a lot of definitions of multivariate quantile functions that are useful, for example, in multivariate quantile regression, will not be such that if you apply it to a bunch of uniforms, you will obtain a sample from pi. Okay, so that's a problem. So there's a question of what kind of inputs are we going to give to the Monte Carlo algorithm. So if we want to sample from pi, we need of course, we need to encode some knowledge about pi into the algorithm, right? So in this algorithm, which I call inverse CDF transform, so inverse CDF because the quantile is the inverse of the CDF, the cumulative distribution function. So that's where pi comes in the algorithm. It's in the choice of the function. Generally, we're going to talk more about algorithms that take the density, so the PDF, as an input. So we're going to assume that we are given a pointwise evaluator of the PDF. And what we want is use that pointwise evaluator and in an algorithm somehow and obtain samples. Okay? But it could be different. For example, there are algorithms that operate with only access to pointwise estimators of pi of x. If you have non-negative unbiased estimators of pi of x, there's a generic algorithm called the pseudo-marginal algorithm that will yield samples from pi, for example. But for starters, we just assume that we have access to an evaluation, a function, basically like dnorm for the normal in R, that gives you pointwise PDF evaluations, at least up to a multiplicative constant, as we see. There are other methods, so I don't know if you're familiar with rejection sampling, for example. Does it ring a bell? Yeah. So for example, if you want to sample from the gamma distribution, like R gamma in R, depending on the choice of the parameters of the gamma, there are two parameters of the gamma distribution, then depending on the specific values, the best known methods to obtain samples are so-called rejection samplers. So in rejection samplers, I'll do just a graph. So you have a distribution, for example, it may look like a gamma. It may look like a gamma to you. It's okay. It's like a gamma. Like some gamma, alpha, beta. Okay, so if you know of a distribution that is above this curve, or this function, a density function that is above, and it could be, of course, that one of them is not normalized, because otherwise they may need to cross, but it doesn't matter really the normalization. So suppose that this is a constant m times the density q of x for some distribution q. Then what you can do is sample basically uniformly under the curve m times q. So how do you do that? You sample from q, so you choose a q that you can sample from. You sample from q, so that gives you the x values here. And to obtain the vertical values, the y values, you sample uniformly between 0 and m times q of x. So you obtain those crosses. And then you decide to retain only the points that are under the gamma curve. And those points, if you look at their x values, they are distributed according to the gamma distribution. That's called rejection sampling. Okay? So you're losing a bit if your function n times q is very far away, because then you're going to reject a lot of points. So you try to find the m and the q such that m times q is as closely as possible above the distribution of interest. Okay? And that can be very complicated, again, in high-dimensional spaces, to find this sort of good approximation, good global approximation of the target. But sometimes it's still feasible. For example, again, if you have a lot of data, you can do asymptotic reasonings in Bayesian inference. The posterior distribution, according to the so-called Bernstein von Mises theorem, will be approximately normal. And so you can then come up with, say, some multivariate students that could be a good global approximation, but above to the posterior distribution, and then do rejection sampling. But it's pretty rare. So usually people do that, again, in small dimension. And then importance sampling. Anyone knows about importance sampling? Yes, more or less? No? No. Yes? Do you want to explain what it is? No.
It's like where we take we want to produce these weights. Sorry, let's produce something.
Okay. Well, it's basically the similar setup as rejection sampling. You have a global approximation Q. You sample from that, but maybe you don't know of a constant m to choose such that, because here the m should be such that pi of x divided by q of x should be less than m for all x. And that may be not so obvious to find this. I mean, that's kind of an optimization problem over x. In fact, you want to maximize this ratio, and if it's finite, then maybe you can find the upper bound. But if you don't want to do that, you can just sample from Q independently, so IID from Q. And then you can define weights. So for each x, and that will be pi of x divided by q of x. So you do a change of measure, basically it's a change of measure formula. So you sample from Q, but you reweight the points according to how likely they should be under pi, but also you want to downweight the points that you sample a lot from Q. Otherwise they're going to be overrepresented. So it turns out this ratio is the right one, and that's quite easy to see because you can, if you have an integral with respect to to pi, you can divide and multiply by q, assuming it's never 0. And so then that means that you could have just another Monte Carlo problem where q now is what you sample from, but you have to weight the test function with the ratio pi over q. So that's all it is. And the benefit is that you don't need to know about this m. But of course, the downside is that you actually don't get samples from pi, you get weighted samples. Okay. Weighted samples. Yeah.
If we were to try and do rejection sampling, but we mess up what m is, and suppose mqx is now going to be, for some values of x, lower than here in the case of the gamma distribution, do we know the result that we get? We know it's not going to be from gamma, but do we know something about it that would be useful?
Yeah, so you have to specify what you do then so what do you do then when, so you have chosen an m, but it may not be the right one. So it may be too low. So the picture looks like this now. Maybe you have a point here, so definitely you accept it, but you basically never reach that area here, so you're going to miss basically some points where there should be more points. Yeah. Maybe you can work out, to some extent, the distribution that you are sampling from when you do that. Yes. It's going to involve, I think, some sort of pointwise minimum. Up to a normalizing constant, it's going to involve some pointwise minimum between pi and m times q, which then you can relate in total variation distance probably to pi. You can probably say something about how distant it is from pi in total variation, because the total variation is the area under the PDFs. So you can say something, I imagine.
And then you get a flag, right? You have to run this to evaluate the Q and the pi. So you know when you've drawn that if that your m is too small.
Yes, in that case you would know, but the problem.
No, because don't evaluate Q.
Well, the problem is that you don't evaluate pi. Typically, you obtain something up to a multiplicative constant proportional to pi.
Okay.
And because you don't know the constant, typically you don't know if you're in that scenario or not. So you need to know sort of a priori that your m is above that ratio. You know that your m will be too small relative to the proportional function that you're using. But then, yes, you will probably, I agree with you that probably there should be some flag that tells you there's a problem. Yeah.
You could do this up to a constant on pi that goes into the m somehow, so you may not have a flag.
Yeah.
You evaluate Q, I think.
Okay, so from inverse CDF to concordance samplings, there's like a gradual like relaxation of conditions.
Exactly.
So I assume from inverse CDF to rejection sampling, it's kind of one time, I would assume, right?
So that's a good point, actually. Usually the inverse CDF, it takes you, in univariate settings, it's always applicable, in a sense, numerically, because you can numerically inverse the CDF. The CDF, you can numerically integrate the PDF to get the CDF. So even from the knowledge of just the PDF, in dimension 1, you can numerically integrate it to get the constant. You can do everything and do inverse CDF transform all the time. So it's only a runtime question, the reason why R gamma doesn't do inverse CDF, for example. It could be doing always inverse CDF transform, but numerically it can be more advantageous to do rejection sampling.
Okay. And for concordance sampling, is it like asymptotically approach like the desired pi, or like how fast?
That's a good point also. So in some settings, if you're interested not in obtaining a sample from pi, but just computing an integral, you don't have to go to the intermediate step of obtaining samples from pi. So it could be that it's faster to do importance sampling, where you weight everything instead of rejection sampling, where some of the points are gone, basically, are wasted out. So it could be that you're better off doing importance sampling than rejection sampling for the same Q, the same function Q. In fact, it could be that it's better to do importance sampling than perfect sampling, because, for example, suppose that your distribution is like this, but you're interested in computing a tail area here. So then sampling from pi is going to give you few points where you want. Okay? Whereas maybe you can introduce an importance sampling distribution that's sort of better placed. So there is some work. So in Arthur Wen's book on Monte Carlo methods, which is good, which I should put a reference on. When it's on his website, there are all the chapters. And there's some examples where it shows that, for example, if you were interested in a tail area, the best possible distribution puts half of the points inside and half of the points outside. So it's sort of located at the threshold, basically. Okay, so yeah, importance sampling can be something that you prefer to do compared to obtaining samples from pi. Yeah.
In all these scenarios, we have to have some sort of knowledge. At least we need to be able to evaluate pi events
Yeah.
at these exits, right?
Yes. Or up to a multiplicative constant.
Okay, if we can do that, I feel like we can already sort of non-parametrically recover this pi
Yes.
somehow.
Yeah, I mean, so I guess fundamentally, if you know the PDF of pi, you know everything about pi. It's characterized by the PDF. It's characterized also by the moment generating function, right? But if I give you the pointwise evaluator of the moment generating function, you may not know how to compute the integral with respect to the PDF. But it is true that it's not surprising that all the knowledge is there. But for example, here's an open question, as far as I know. If you are given pointwise evaluation of the gradient of the log density, there should be all the information about the pi in there as well. Because you are losing the multiplicative constant, but you know it integrates to 1 anyway. So if you know that everywhere, you can do, in principle, there's only one pi that corresponds to this function, right? And yet, there is no Monte Carlo method that I know that takes only this as an input, and even asymptotically recovers pi. It's possible that there is one, there will be one, but it's not known. Whereas, for example, you can optimize, of course, with gradient descent and get the maximizer of pi of x with this. So and so indeed, you could sample, you could do a grid, evaluate pi everywhere, and then non-parametrically interpolate between the points in the grid, and in the number of points, you will recover everything about pi. It's just not the most efficient thing to do in large dimension. We good? Okay, so what we're going to do is we're going to construct Markov chains. So that's a way of going beyond what we can do easily with importance sampling and rejection sampling. In particular, because we won't have to know about a general good approximation of pi on the whole space. So maybe we'll rely only on sort of local information about pi, local perturbation, in order to obtain globally a sample distributed according to pi. So schematically, we're going to sample first anywhere. So we're going to start from some distribution pi 0. It could be, for example, the origin in the state space, the vector of zeros. And then we're going to progressively change x0 to obtain x1, and then change x1 to obtain x2. We're going to do that randomly. So that's going to define a Markov chain, a Markov process. So Markov in the sense that when we're going to obtain x2, we're only going to modify x1 and forget about what comes before. There are some other methods, for example, so-called adaptive MCMC methods, that employ the whole history of the points that we have generated. But we're going to focus on the simpler Markov chain case. And we're going to do that capital T times to obtain xt. That's going to be approximately distributed according to pi if we do things properly, if we design the algorithms adequately. And in a sense that will be to be defined more precisely later. And so here we're going to work on discrete time in passing. Of course, you could, in principle, operate on continuous time. And there are, in fact, algorithms. For example, in the Monte Carlo literature recently, there were a lot of piecewise deterministic MCMC algorithms it's a reference here, and those operate on continuous time. It doesn't have to be, so the state space could be discrete or continuous, the time could be discrete or continuous, but mostly the time is discrete in that literature. Okay, so there's going to be various questions we're going to try to touch on in order to, again, understand the inputs and the outputs of those algorithms. So in the output, the simplest way of running those algorithms is to do a long run. So you basically do those steps for as many iterations as you can. For example, you leave the office at 5, you run the algorithm, and you come back to the office at 9, and it has done 2,000 steps, and so that's your number of steps for today. Okay? But the validity of the algorithm would typically rely on this t, this number of steps, to go to infinity. So you could be tempted, especially in the era of parallel computing, to go on Amazon Cloud and to ask 1,000 machines to perform this in the same amount of time. So again, from 5 p.m. to 9 a.m. the next day. Each of the machine still does approximately, say, the same number of iterations that you will have done, but now you have 1,000 chains. Okay? So that should be helpful for something. And so in particular, if you average the results over the different chains, so the IID across the different machines, so you're going to reduce the variance by the number of machines. You're going to divide the variance by the number of replicates that you're doing. The problem is the bias, right? So you're going to kill the variance by averaging over independent copies. But if there is a bias, averaging independent copies will not reduce it. Right? So that's the problem. So that's why you don't do a million times one step, and you still want to do enough steps. Right? It's the same with optimization. Right? Typically, the guarantees are obtained iteratively. And that's a big problem at the moment in particular because the machines are not getting much faster, but we have more of them. So in terms of clock speed, the number of gigahertz, that's sort of more or less proportional to the number of iterations you can do in a given time. That hasn't been going up very much lately. So that was different in the early days of Monte Carlo, where you could just wait for the next year's computer to do twice as many iterations as this year's computer. And so that was fine in the sense that the algorithm would rely on asymptotic regimes like that. But nowadays, you would like to leverage more and more machines because there's really fundamental limits in the clock speeds.
I was going to ask, related to a few long runs versus many short runs, if you don't mind going back to the previous slide.
Yeah.
So we started from x0, applied random perturbations, got x1, do the same thing all the way to xt. For t large enough, xt would be drawn from pi. If we took a look at x cap t minus 1, let me now construct a different MCMC chain that where the new pi map is going to put all its mass on this x cap t minus 1. So the first sample of this new chain is going to be x cap t minus 1.
Mm-hmm.
If I were to apply the same sort of random perturbations to x cap t minus 1 as I did in the original chain, it feels like the new x1 that I would get would be the same as the x cap t that I would get in the original sampler.
Yeah.
So it would be then the case that the large enough cap t in this new sampler is 1?
Yeah.
Okay.
But you will get only one sample from that.
Right.
So for example, that's so just to be clear, so if you look at the trace of the chain, right? So you start from say x0 and you run a markup chain, so trajectory is like this. And xt, your hope is distributed according to the distribution pi. Now, if you start from xt, then it's like starting from pi. But if you started many, many chains from xt, it would not give you IID samples from pi in one step. It would give you always, from there, marginally it would be from pi. But if you start independent chains from there, they would probably be after one step quite close to xt. So they would not give you a whole sample from pi. You see what I mean? So having one sample is only going to help you warm start one chain, in a sense. Okay, so this problem of bias, basically, the bias that comes from not having started from pi independently, having started from pi 0, is sort of the main problem in trying to parallelize MCMC. If you could sample from pi from the beginning, you could do that on many machines. That has been well recognized for a long time. Okay, so that's, I'm announcing this as one of the problems we'll try to address with this so-called coupling machinery. So we'll see a classical algorithm called coupling from the past, and that's from 1996, that employs coupling to obtain perfect samples from Markov chains. And then we'll move on to more recent estimates that are due to Peter Glynn and Chang-Han Ri in 2014.
Pierre,
Yeah.
just another clarification question. If we are able to start sampling from pi at the get-go, then is it, if I'm understanding correctly, that we don't have to worry with this finite time bias? So if I were to run one chain, get x cap t, and then start parallel chains from x cap t as you were describing there, would that take care of the finite time bias, or do we still worry about finite time bias?
No, so it's quite subtle. It's hard to write, but if you have xt that is distributed according to pi, and now you run, say, xt plus 1, 1 to xt plus 1 r, you sample them from what we want to denote by p of xt dot. Okay, so you do one step of MCMC starting from xt, but you do it many times in parallel. So marginally, they will all be from pi. If you do it once, or if you do it r times, it's the same. They're all from pi, but they're not independent. They're not independent from pi. And so, in fact, they could be all very, very similar to your xt, and pi could be very different from a Dirac mass at xt. Right?
Maybe I misunderstood the question. I thought the question was, what if we start all the next chains from the drawing from x0 to xt?
Yeah.
We have one chain, we have a sample of pi, and then we start all the 9,599 chains by drawing on the side points randomly from the first chain.
But if you draw every time the starting point independently from pi, then after one step, you get a point that is still distributed as pi, but now it's independent from the other. So that's fine. So if I draw independently even from x0, another point, and I have another trajectory, and now I get another xt, and those two xt's will be more or less independent points from pi. But the problem is if you start always from the same guy, you still maintain marginally the fact that it's distributed according to pi. But now, of course, you can imagine that they're not going to be distributed far away from in one step from the previous point, so that's not going to solve your sort of integration problem. But if your point is only to get, if your goal is to get non-independent samples from pi, then that's fine. But typically, that's not what we want. So it's quite subtle, but probably we'll go back to that, yes?
So, for your second run, can you start from the same X naught, but just set a different C?
Oh yeah. If you do a lot of steps, it's probably the same if you start from the same x naught or a different x naught.
Then can you start from the same XT, but just set different seeds, and then after like a certain amount of time, it's like pi,
Oh yeah.
basically?
You're right. So if I do, again, a lot of steps, then they will sort of disperse and be nearly independent from pi. The problem is one step now, unless your MCMC algorithm is so good that it only requires one step.
Is the number of steps that's needed for the like new point of the ID less than
That's a
starting
very
from
good point, yeah. So I guess there's two things. There's getting marginally from pi, and there's sort of forgetting the initial point.
Yeah.
And it's true that technically you could define those things differently, but then for typical Markov chains in MCMC, essentially it's going to be the same time to go from anywhere to pi or to be independent of your starting point. But it's true that it could be different for other processes. Yeah.
So for the long run, like you summed up all the different time steps.
Yes,
But for the parallel run, like
I didn't.
just
Absolutely, yeah. Yeah, you're right. You could average over the times and then average over the copies. I was just saying that if you were to do R going to infinity asymptotic here, in a sense you would always get, I mean, you wouldn't have to even average over the times because you would get perfect precision if T is large enough from just the last guy of each chain. But it's true that in practice you'd want to not waste all those points before, and so you'd average over time, and then you'd average over the repeats. Okay, so let's try to come up with examples. So this is kind of an exercise, yeah, Guillaume?
Yeah. So actually what I had for, so if I'm just trying to get independent samples, I can like shop, go along the chain with long enough that I think
Yes.
my next sample is independent.
Yeah, you could imagine that if the time in between is very large, they're kind of independent of one another.
Is there a formula we think about how whether I even want to do that or how I want to do that if I'm interested in the integral?
Yeah, that's a good point. So that's called thinning in MCMC.
Right.
Thinning the chain is to retain only some of the points along the chain.
Like I would want to keep more points if I care about the integral and if I care about producing a sample of points per point.
Yeah, absolutely. So in fact, so if your goal is precision of the average over time, then there is no point in dismissing samples. Right? You should keep all of them. But if the question is, because your memory is limited, for example, or maybe your test function h is very expensive to evaluate, and so in that case, it's better to do a lot of steps before you evaluate it, and to keep only, so there's actually a very good paper of Artowen on this. But typically, h is instantaneous to evaluate, it's an indicator function, and running the chain is very long. And so it's better to keep, especially you can, you can compute a sum like this on the fly, right? So you don't need to store anything. So if your goal is the approximation of an integral, there's no memory issue. But if your goal is to find, you run 1,000,000 points, 1,000,000 iterations, and you want to best 1,000 points that are representative of pi, you should not keep the last 1,000, you should sort of equispace them. It's called thinning. Okay, so here's an exercise. And so, you have a distribution which is non-standard, still in one dimension. How do you obtain sample from it? Maybe you can come up with a good global approximation and do rejection sampling, for example. Or you can start from a point, x0, and then try to think about how you're going to construct x1 and then x2 and then x3 and so on, in such a way that if you do enough iterations, the samples are going to be distributed according to pi. It could be a good exercise to really, even if you know already a bit about MCMC, to restart from there and think about what can you possibly do. So this distribution, if you plotted the curve, it looks like this. Kind of a wiggly perturbation of Gaussian. And you start from x0. Okay, so we're going to try to come up with a Markov chain that will converge to pi. So do some sort of local modification of x0 first. So we want to move. So what can we do to move? Propose a move. Yeah, you could imagine, let's sample, we're going to call it x star, centered at x0, and with some tuning parameter sigma square. Right, so maybe we run it and then we end up here. But if we are saying x1 equal x star and continuing to do that, it wouldn't work, right, obviously, because we have not used pi anywhere first here, so that's a bad sign. And also it's a random walk, right, so we know that in fact it would not even have an invariant distribution, it would sort of diffuse in the whole space. And so what we can do is we can propose these points, but not necessarily define x1 to be that point. We can decide if x1 is going to be that point or not. Okay? So that's going to be the so-called Metropolis-Rosenbluth-Taylor-Hastings algorithm. So most people call it just the Metropolis algorithm or Metropolis-Hastings. But I call it this instead. So I'm going to talk about why later on. It doesn't catch. I've been calling it for a few years. It's not sticking. But So we propose, okay, so we just did that. We're proposing X star from a proposal distribution, which could be just a normal centered at X t. So now we are at time t, and we're imagining how to construct t plus 1, X t plus 1. And what we're going to do is either we're going to set X t plus 1 equal to X star, or we're going to define X t plus 1 to be equal to X t. So there's always going to be an X t plus 1. So all we're going to do, we're going to do one step. It's not like a while loop. We're doing one step. But because the new point could be exactly the same as the previous point. So the trajectory could have some sort of flat horizontal lines. And what do? We accept these points if, so with probability given by minimum between 1 and this ratio. So it's something uniform and comparing it to this ratio. And this ratio, it has some pi in it, so that's good news. We're using pi now. It has a ratio of pi's, in fact. So pi evaluated at the new point, the proposed point, and pi evaluated at the current point. So you see that because it comes in as a ratio, any multiplicative constant here would cancel out. So we don't really need to know exactly pi, but any function proportional to pi would result in exactly the same decisions to accept or not. And we want to also take into account the proposal distribution, because if we are more likely to propose some places, then probably we should discount the acceptance of those points. And so if you actually sample from a normal center at the previous point, so you have some symmetry, right? And so this ratio of q's would cancel out. So we would accept or not only based on the ratio pi of x star divided by pi of xt. So basically, if pi of x star is larger, you will accept. If you propose a point that has a larger density, you will accept. That's not the case here. Here we're proposing a point that has a smaller density. And we may still accept. Okay? So in a sense, that's a difference with optimization, with basic optimization. With optimization, we try to find a better place. But here we may want to accept a point which has a lower density because we want points everywhere, right? We want more points where there's high density, but we also want some points, especially if you're going to have a lot of points, some of them should be in regions of lower density. So this ratio sort of hopefully makes intuitive sense. It may be not clear why it's exactly this formula and not another formula. Right? It could be all sorts of formulas that would still be valid, in fact, but this one is special, and so this is the one in particular exactly in that form. It's in the paper of Hastings in 1970. So the Rosenbluth in the name, Metropolis Rosenbluth Taylor Hastings, only passed away a few years back during COVID, but she was in her 90s. And she's the one who implemented it in 1953 on the MANIAC computer, so that's in Los Alamos. And usually in algorithms, it's the person who implemented it who really understands what's going on. So I think it's probably the person who really understood what was going on in the 1953 paper, but her name was sort of dropped out of the. People usually call this the Metropolis algorithm. She's the first author in that original paper. And that's the guy who had the computer. That's the director of the lab. So his name was automatically in every paper. Apparently, he didn't do anything on that particular paper. But he's a famous physicist who did a lot of other things. But Rosenbluth did the implementation, so probably she understood what was going on. She was also amazing in different ways. She did the Olympic Games in fencing for the US team, and she was one of the first few people to get a PhD in physics. She was the 5th in the US or something like that, among women in the US. Okay, so that's the name of the paper, Equation of State Calculations by Fast Computing Machines. So Metropolis, Rosenbluth, Taylor, and Taylor. And that last Taylor is a famous physicist who is in Oppenheimer. He's the bad guy in Oppenheimer, who's betraying Oppenheimer and calls him a communist, and he gets into all sorts of problems. So that's the last guy in that paper. So they're all working on all sorts of Monte Carlo methods, and this one is the first to propose a Markov chain approach. Where you don't come up with a good global approximation, you start somewhere, and the problem has to do with packing. So you have a square, and you want to sample so-called hard disks. So those are disks with a radius, and they cannot overlap. Right? So you want to put a certain number of those balls in a square. They are not allowed to overlap. So in the problem, there was a certain choice of radius. Let's say that the square has left 1, and they were operating with 224 instead, let's start from this packing. We deterministically obtain the packing, which is basically these adjacents. Take the least amount of volume. And then you're going to try to modify them, to move them sort of locally. So you're going to take each of the balls and you're going to propose a new center for it. And if it doesn't clash, if it doesn't intersect with the other balls, you accept. Okay. So the original problem was already quite hard, I would say, because in fact the dimension is 224 times 2, because each ball has a two-dimensional xy coordinate. So it's quite a large dimensional problem. And they did 64 iterations. They explained in the paper that it took already days. And that was that. There was no sense that it was enough iterations. There was more like the number of iterations that they could reasonably do. And so that's what they did. And they do also, they do a run with like 32 iterations, 64 and 96. And they see that the estimate doesn't change so much between 64 and 96. And so they are sort of happy. But they could have been that they found a sort of local mode. They wouldn't. And so in fact, what's interesting about this, I think, is the convergence analysis of this particular algorithm, the very first in the literature, is nowhere. So the closest that I find is this paper by Diaconis, Lebeau, and Michel that analyzes a simpler version, in fact, of this algorithm. But the analysis of the original algorithm is an open question. Like how many iterations does it actually take for the algorithm that they propose to reach stationarity? So the interest has moved on because now people use different algorithms to solve those kind of problems. And so it turns out that no probabilist has solved exactly this question. Okay, so the general ID and what we've just seen with the Metropolis Rosenbluth-Taylor Hastings is a particular case. There's many other constructions to obtain a convergent sequence of points that will go to pi. And the general idea is that you will try to obtain a fixed point iteration on the space of probability distributions. So you will change the distribution in a way that you know that if you arrived already at pi and you do one more step, you would remain at pi. So there would be some sort of fixed point phenomenon. So if you write pi t, the marginal distribution of xt at time t. So you start from pi 0, then you do one step, and marginally the distribution of that point is pi 1, and then it's pi 2, and so on. And you denote by px dot the conditional distribution of xt plus 1 given xt equal x. And that's the same for all t because we say we use the same algorithm repeatedly, right? So it's a homogeneous Markov chain. So capital P here describes the distribution of the next point given that the current point is at little x. Okay, so by definition we can write the marginal distribution after one step as what happens when you start from pi t and do one step with p. So in terms of integrals, the mass of pi t plus 1 around px prime, you integrate over what would have been the previous step. The previous step is around pi t, and then you need one step to arrive around dx prime. So if you want pi t dx px dx prime here on the right, that's the joint distribution of two consecutive steps. So if you integrate over the first, then you end up with the marginal of the second. That's it. And so by construction, those instance algorithms are pi invariant. So they're constructed in such a way, so this ratio that we've seen in the acceptance decision is exactly such that if you were already distributed according to pi, after one step you will still be distributed according to pi. Right? That's not enough to guarantee convergence to pi, but that's a good start. That's a good start. Okay, so you can say more about the transition kernel, so this capital P, for the specific Metropolis algorithm. We can write it in this way, so it looks a bit nebulous perhaps. So there's a chance that you remain at the same point as before. That's if you reject the proposal. So with a certain probability that depends on where you are, R of x, so that's the rejection probability, your next point is following a Dirac mass at x. Otherwise, it's distributed according to Q, but weighted by this propensity to accept those points. So that's alpha, that's the acceptance ratio, basically. So R of x, you can write it in terms of Q and alpha. R of x is the probability of rejecting a point if you start from x. So it's 1 minus the probability of accepting a point, and that's the probability of accepting a point is, well, you're going to propose them from Q, and then you're going to accept them with the given ratio. And so in fact, it's a probability. So you have this ratio of pi's, and then there's the ratio of the Q proposal. Dx prime. So the minimum one, is that clear where it comes from? It wasn't in the algorithm because we don't need it in the algorithm. Right? If you draw U from a uniform, it will be less than 1. But the probability of accepting cannot be just this ratio because this could be larger than 1. So the probability of accepting has to be the minimum between 1 and that. Okay, so now you can check that indeed this satisfies the so-called detailed balance condition. So that's pi of x p x x prime is equal to pi of x prime p x prime x. And that in turn implies the pi invariance. So it's very easy to see the last point here. So if you have detailed balance, you have pi invariance. Because, so if you, pi invariance is the fact that pi of x prime is equal to the integral of pi of dx p x x prime. Okay, so I'm going to write it more simply with pi of x dx. But if you have detailed balance, it's clear that this thing would then be equal to the integral of pi of x prime p x prime x dx. And so if you have detailed balance, you have this equal that for all x prime. So you can integrate. And then when you integrate, you realize that you're integrating just this x here. But because p is a conditional distribution, it integrates to 1. So you're left with just pi of x prime. So you've just shown pi invariance. It's a good exercise to do. It's kind of nearly automatic. So that's the way that SLC algorithms are designed. You try to get detailed balance, and then you know automatically you get pi invariance. Most algorithms, like 99.9%, will satisfy detailed balance. There are some exceptions. You can be pi invariant without satisfying detailed balance, but mostly it's constructed that way. So it remains to check that this ratio is the acceptance probability is such that you do have detailed balance. Okay, so because of the form of p of x x prime at the top, it's obvious that for x prime equal to x, you will have detailed balance. You have pi of x, then you have r of x delta, an indicator that x is equal to x prime. And so because you have an indicator that x is equal to x prime, you can put x prime or x as you want. And so you have the equality on both sides. What's not so obvious is that it's also the case when x is not equal to x prime. I'm going to check that. I think it's important just because this ratio is not, it's not magical. It's acceptance probability. It comes from having constructed it so that it satisfies this. And so you want to show in the case of x different than x prime, you have, you're in the right-hand side of the formula at the top. So you have this. Okay, so now you replace the form of alpha by what it is, so the minimum between two things. So you have the minimum between q of x, x prime, and this is going to cancel out something that was at the denominator. So now you have pi of x prime over pi of x, q of x prime x. Right, so now you can put pi inside as well, if you want. So here I just, there was a 1. There was a 1, a minimum 1, and the ratio. I put that q of x prime inside. So I have this. But then I can also put pi of x inside, so on both sides. So then I have this, and I can erase the denominator here. that's basically symmetric in x prime. So you have detail balance, and so you have pi invariance. So at least if you start from pi and you do one step of this scheme, the point that you get is still distributed according to pi. So it could be different. So there are other acceptance rates that would satisfy this property as well. Interestingly, so in 1973, Esken was the PhD student of Hastings, proved that in fact this ratio is in fact the best in the sense that for a given choice of Q, if you use this acceptance rate, you will have the best chance of accepting while still being pi invariant. And having the best chance of accepting, so the maximal acceptance rate, in turn, that's the theorem, leads to a minimal asymptotic variance for the estimators.
In a class bigger than reverse detail balance.
No, I think looking at all the acceptance rates that are leading to a pi invariant, the detailed balance condition.
That's a very small class. Because if I want detail balance and I'm looking for my acceptance probability and eventually same thing, I can almost derive. I think I can derive this.
You can derive it, but you can derive another one as well.
Okay.
So, for example, the Barker one. So there was some doubt because people were using either that one or this one. So the same numerator, but at the denominator you had the same thing plus the symmetric one. That's called the Barker's acceptance. So that also is valid, for example, but you accept less, and so you get.
And you have detail balance.
And you have detail balance. And there may be others. Yeah. Okay.
Can I ask you a quick question just to make sure that I understand? I mean, you mentioned this thing about the kind of like the fixed point of an operator. So just
Yeah.
to make sure that I understand the terminology. So start with the transition kernel.
Mhm.
Right? Like it's the probability of xt plus 1 given xt. So that's the
Yeah.
transition kernel. And essentially you're using that transition kernel to define this operator, right?
Yeah, yeah, absolutely.
Some distribution pi of t.
Yeah.
And you pass it through this integral that is defined by this transition kernel, and that spits back some pi t plus 1, right?
Exactly.
For each value. And so when you write the proofs of convergence, just like, what exactly do you show? You show that you look at the distance of pi t plus 1, evaluating suppose that these are actually PDFs, so I don't have to do the dx, I just have
Yeah.
like pi t plus 1 of x prime minus the true pi of x. And what do you do the sup over the support?
Yes.
Take the limit, or are these things pointwise? Or how do you think?
The-
Just thinking about what type of statements you actually get from this.
Yeah, so tomorrow in particular we'll look at specific statements, but typically convergence in total variation, which is the integral of the difference between the PDFs, or in the Wasserstein distance, so the optimal transport type of distance, which is in 1D would be the integral between the CDF. So CDF, PDF, that sounds like the same, but it's convenient to work with. And then there are results in Kullback-Leibler, there are results in Prokhorov distance, and depending on the algorithm, whatever is more convenient. And of course, there are some generic relationship between the distances, but TV would be the most used metric in MCMC, I would say.
Yeah, so just in terms of the theorem would say something like, suppose that the kernel that you're using satisfies these pi invariants.
Right.
Then the limit of the total variation is pi t equals 1 relative to pi. T goes to infinity, goes to 0.
Goes to 0, that's the basic. But then, of course, you want to know the rate of convergence and all that stuff, yeah.
Okay.
And we'll see that we need more than pi invariance. So a very simple example. If P of x dot is the Dirac mass on x, so your chain is staying wherever it is, actually that's pi invariance, right? So you take a draw from pi, you do nothing, and you get a draw from pi. So clearly we need something more, right? But in fact, not much more. Okay, so there's all sorts of things that are interesting about this particular acceptance ratio. So it leads to the best. So I need to check about in which class. But somehow it's better than markers, but it's somehow supposed to give a good asymptotic variance for your estimates. It's also, in a certain sense, the minimal deviation from your proposal. So your proposal distribution that could have been the normal centered at the current point. So that's a Markov kernel, but that is not pi invariant. So you can imagine, okay, let's project that operator onto the space of pi invariant operators. So find the closest, the least, the smallest modification that you can do to it in order to be pi invariant. And in a specific sense of distance, in a specific definition of distance, you do get again this metropolis Hastings chain. So that's proven in Villela and Jack in 2001, and it's used in recent proofs of convergence for variance of metropolis Hastings. But the distance is a bit complicated, I would say. So it could be that, by the way, it could be that if you change, if you pick your favorite distance between two transition kernels, and you do the same type of projection, you find a new algorithm. And here is really projection onto pi invariant Markov kernel. So it could also be that you find a kernel that is not satisfying theta 1 or line. But, so this distance, so how do you compare the two different Markov kernels? So here it says that you look at the difference, assuming everything has a density. You look at some integrated distance between the PDFs, from x to x prime according to the two kernels, but you integrate that with respect to pi for the starting point. So that gives you a metric on the space of transition kernels that are pi invariant, or even not pi invariant. Okay, so we just talked about the most basic algorithm, the one from 1953. But in fact, the one from 1953, it didn't do exactly what I just said. So if you go back to that. So here the state space would be the x and y position of all the poles. And so you could say the basic application of metropolis Hastings to that would be to propose, say, a Gaussian deviation of all of those coordinates at the same time and decide to accept or not. But that's not what they did. Quite intuitively, they delete one ball at a time. So they select just one ball, it's a two-dimensional problem, they propose another position and they accept it or not. And then they move to another ball and then they sweep through all the balls like this. So this now would be called a Gibbs sampler. A Gibbs sampler is when you don't change everything, you go sort of component by components or blocks of components at a time. And that's convenient because it's easier to get decent acceptance rates when you're looking at a smaller dimensional problem. So it's a way of dividing a big problem into lots of small dimensional problems. So that's called Gibbs sampling. And of course, there's a lot of questions now. People are still debating about whether you should do a random order of the updates or a systematic order of the updates, for example. Is there a best order of the updates to do? Of course, it's also not clear always that you should do the same number of updates for each of the components. So in the hard disk problem, everything seems symmetric, so why prefer one ball compared to another? But for example, if you're doing some sort of Bayesian regression, you maybe have some components correspond to the regression coefficients. Some components maybe represent the variance of the noise. Maybe it's a good idea to update many times the variance of the noise before you re-update the regression coefficients, for example. So there could be lots of tuning parameters involved in an efficient algorithm. There's also a systematic way of addressing a certain problem called slice sampling that operates with an augmentation of the state space. So for example, if you want to sample from this distribution with density exponential minus square root of x over 2, there's a very nice slice sampler that, so you could do what we've just proposed with normal deviations accepted or not. But you could do something where you introduce a variable u, which given x follows the uniform between 0 and pi of x. Okay, so you have the original problem, now you have a new You augment the state space to include this u variable. And now you can work out analytically the formula for x given u. And you realize that, in fact, you can sample from that. I think if you work it out, it's a uniform distribution as well. And so now you can have an algorithm that alternates between updating u and updating x in such a way that if you just look at the x components, it will converge to pi. So this idea of like updating components at a time is quite powerful, basically, to address all sorts of problems. It's a good trick to have. Another classical problem is the probability regression model.
One quick question, sorry, but in that case, in the previous example, we knew that I is constant, right?
Right.